Okay, let's look at the heat capacity for an ideal gas. And we're going to look in terms of the molar heat capacity and why the molar heat capacity at constant pressure is different from the molar heat capacity at constant volume. We're going to look at, I guess the easiest ones to look at would be the isochoric process and the isobaric process. The isochoric, of course, the volume is kept at constant, a constant level. We simply change the temperature and therefore the pressure changes. Isobaric, we are keeping the pressure at a constant level. We know from the previous cases, the molar heat capacity at constant pressure is going to be greater than the molar heat capacity at constant volume. Okay, here I am writing the first law of thermodynamics for an infinitesimal amount of volume or whatever within an ideal gas. Now, it's written like this, basically, although we're more familiar with delta U being equal to Q minus W. So we're saying for this infinitesimal amount of volume within this thermodynamic system, the change in internal energy is going to be equal to the heat added to that particular volume minus the work done by that volume. Now, for the case of isovolumetric, we say that the work done is zero because there is no change in volume. So we're going to look at that case right here. We're going to say, okay, let's set dW equal to zero and look at the change in internal energy as a function of the heat. Well, that's pretty simple, right? The heat is equal to the number of moles times the specific heat at constant volume. Again, constant volume, we're not doing any work, volume's not changing here, times, this should be probably a dQ, but times the temperature, okay? Again, I think that should really be a dt there, but that's fine. So here is our change in internal energy for that particular case. Again, this is from the isovolumetric or isochoric process. Now we're going to do it again, but this time we're going to do it at constant pressure, okay? We know that the heat added to that particular location is going to be equal to the number of moles times the molar heat capacity at constant pressure times dt, okay? Change in temperature. So that should have been a dt previously. Now, the infinitesimal work, okay, at constant pressure is P delta V, okay? Or in this case, we're writing it as P dV. By the ideal gas law, P V equals nRT, okay? But we're doing this by infinitesimal steps. There's an infinitesimal change in volume would be proportional to the number of moles times the gas constant times the infinitesimal change in temperature. Okay? So, looking at all of this, here is my dq, here's my dw. Okay? So I'm going to take dq and put it right there. du is equal to dq minus dw. You already wrote that before. Now I'm going to take this, I'm going to put this right here. All right? Notice the difference between the two. Both have n, both have dt in them, okay? The difference is Cp and R, okay? So we have n times dt, Cp minus R. And that relates our molar heat capacity at constant pressure to our molar heat capacity at constant volume, which we got during the first case. Okay? So what can we do with this? Well, Number of moles can cancel out right there. dt can cancel out right there. And we get a relationship between Cp and Cv. Okay? And again, that's where that comes from. All right? Cv, the molar heat capacity at constant volume, is 1R less, one gas constant less than the molar heat capacity at constant pressure. Okay? Or you can write this the other way. Cp is equal to Cv plus R. And again, one way of thinking about why this happens is if we have a pressure versus volume diagram, okay, to change temperature at constant volume just takes internal energy. To change temperature at constant pressure, not only do you have to change temperature, but work also has to be done. So naturally, we would accept that, yeah, Cp, molar heat capacity at constant pressure, has to be greater than the molar heat capacity at constant volume where no work is being done. Okay? Again, not so important for what we do here, but it shows you why those two are different. It derives why those two are different, albeit using calculus. And again, for those of you who aren't taking calculus, is not a calculus-based course, but it's good to see where this actually comes from. Okay, molar heat, specific heat capacity at constant volume for a monatomic gas is this right here. Okay, and of course, Cp would be plus R additional to that. So 5/2 R. Okay, for a diatomic gas, because there are more degrees of freedom, and we saw this in the other chapter, the previous chapter, Cv is equal to 5/2 R. So if you want to write Cp, Cp for a monatomic gas is equal to 5/2 R. I just add an R to this. I add an R to this, and Cp for a diatomic gas would be 7/2 R, just another 2/2 that we add to that. Okay, so a diatomic gas is going to have more opportunities to store energy because of rotational and vibrational modes than that of a monatomic gas. I got to be careful there because, as we saw in the previous chapter, some of these don't kick in until higher temperatures. Now, again, we look at these values for different gases. And again, this is assuming an ideal gas. Here again is Cp, here's Cv. Let me just change colors here. Monatomic, so like, helium, neon, argon, these would all approximate these pretty well. Again, the difference is just R between the two. We go up to diatomic, we bump up by another R, okay? And then for polyatomic, we can go up to, well, approximately 4R. Got to be a little bit careful there because the dynamics of the molecule are going to affect that. But this agrees pretty well with what we observe for real gases. Again, here is our Cp for the noble gases. Okay, just flip back here quickly. We estimate 20.79, and wow, that's pretty much right on the dot right there. And again, Cv should be 3/2 R. So go back to the previous case, 12.47 and 12.5. You see a little bit of deviation with neon and krypton, and that's not unexpected. their van der Waals forces are a little bit greater. But again, the difference between CV and CP are pretty much close to R. Okay. Now for the diatomic gases, we start seeing a greater deviation. I guess hydrogen would be the best representative of a diatomic gas that was as close to an ideal gas as possible. So here we see, well, let me erase some of these other ones. Here we see at 28.8 and 20.4. Those are the actual measured molar specific heats. Going back to the previous slide, for diatomic gas, CP should be about 29, CV should be about 20.8, and yeah, they're very, very close. Actually, nitrogen does a pretty good job. 29.1, 20.8. Nitrogen. Okay, very, very close to that. Oxygen, not bad either. Okay, so these symmetric diatomic gases actually do pretty well there, and that's not surprising. They're not polar, right? But as soon as we start getting into some of these polar molecules, obviously this is going to break down. Chlorine is not polar, but certainly carbon monoxide is polar. 29.3, 20, that's pretty good. Not quite sure, I wish they used, a diatomic gas that was polar. But here they use chlorine, which is much more massive. Okay. Deviates pretty well from these other figures. Polyatomic gases. Here we said that CP was roughly 4R or 33. What do we get for CP here? A bit higher than that. And again, we're starting to see the emergence of these van der Waals forces. We expect 33. We see higher numbers here. CV should be about 25. And, obviously we're off there too. Okay. So that's where these numbers CP and CV come from. And again, they do a pretty good job giving us approximations for what the molar specific heat is. But again, real gases are much more complicated.